Hi, good afternoon to all. I, S. Nagaraju, on behalf of Triple E Department of ITAM, Tekkali, would like to invite Session 8 on Day 3. It is my immense pleasure to introduce Dr. Prem Kumar, Speaker of Session 8 on Day 3. Dr. M. Prem Kumar has received BE degree from Sri Ramakrishna Institute of Technology, Coimbatore, India, and ME degree from Anna University, Coimbatore, India, and received his PhD degree from Anna University, Chennai, India. He has more than 12 years of teaching experience, and currently he is working as an assistant professor at GMR Institute of Technology, Rajam. He has published more than 60 technical papers in various national, international peer-reviewed journals, including IEEE, Elsewhere, Springer, etc., out of which 17 papers are indexed by SCIE and 34 papers are indexed by Scopus. He has also presented 28 technical papers in national, international conferences at different venues. He has filed patents with Indian Patent Office and Australian Patent Office. In addition, he has also offered consultancy services to various industries. He is serving as an editor reviewer in reputed journals such as IEEE Access, IET Power Electronics, IET Renewable Power Generation, IET Science, Measurement and Technology, International Transactions on Electrical Energy Systems, the Journal of Electrical Engineering and Technology, Electrical Engineering, Measurement and Control, International Journal of Green Energy, and other Scopus indexed journals. He has hands-on experience with hardware development boards such as Opal RT, DSpace, Arduino, and Raspberry Pi. He can also work with software tools such as MATLAB, Simulink, PLECS, Typhoon Hill, PSIM, and PVSys, etc. He can design and develop DC-DC non-isolated isolated buck-boost converter for electric vehicles, single-phase standalone grid-tied DC-AC inverter, solar PV MPPT controller, and battery charger controller. His current research field includes solar PV microinverter, modern solar PV MPPTs, solar PV parameter estimation, PV array faults, non-isolated isolated DC-DC converters for electric vehicles and PV systems, and optimization techniques including single objective, multi-objective, and many objectives. I would like to thank you, Dr. Prem Kumar, for accepting our invitation as a guest of speaker for today's session. Now I will hand over the session to Dr. Prem Kumar. Thank you.
So thanks for your wonderful introduction, sir. So let me share my screen. Shall I?
Yes, sir. Yes.
Yeah.
Kindly share your PPT.
Yeah, sure. I hope slide is visible, right?
Yes, sir. Yes, sir.
Yes, sir.
Yes, thank you very much. So before starting my session, first I would like to thank the head of the department and the management principal and management of Aditya Institute of Technology and Management for giving this wonderful opportunity to discuss on DC to DC non-isolated converter topologies in fuel cell vehicles. I myself, Dr. Prem Kumar from GMR Institute of Technology, Srikakulam, Andhra Pradesh, India. So I'll move on to the session now. So before starting the session, so I would like to give the outline of today's presentation. So let me start the today's session with introduction to the fuel cell based electric vehicles. So here what I'll be discussing is I'll be discussing some different fuel cells available in the market and which fuel cell is particularly suitable for transportation application, and I'll be discussing on the different classifications of the fuel cell based electric vehicles and the bottlenecks, the major bottlenecks of the fuel cell based electric vehicles. I'll be discussing in the introduction to the fuel cell based electric vehicle section. And next I'll move on to the responsibility of power electronics in fuel cell powertrain and its classification. So here what I'll be discussing is why power electronics is required in fuel cell powertrain system, and also what are the classification in general, how the power electronic converters are classified. So what are the importance of each converters, that I'll be discussing. And the classifications are here. The one important thing is when we discuss the fuel cell or the electric vehicle, uh, we'll be having two different types of the converters called, the bidirectional converters and the unidirectional converters. So this whole session, I'll be discussing only on unidirectional converter. Okay, so maybe the people aware of the bidirectional converters. So mostly the people will be discussing on bidirectional converter. Some only very few researchers will be discussing on unidirectional converter. So my focus, this session focus is only on unidirectional converter. And also when we discuss about the converters, we'll be having two different types of converters, the isolated converters and non-isolated converters. So here the whole focus is on the non-isolated converters, and also it's a multi-stage power converters. It is not a single stage. It is not like the conventional buck or boost converters. It is a multi-stage converters. So I'll be discussing the unidirectional, non-isolated DC to DC multi-stage power converters. So in that, we'll be having different classification. So the first classification is multi-stage switched capacitor-based converters. So we have some boosting techniques in non-isolated converters. So the very first the technique or boosting technique called switched capacitor. So first I'll be discussing on switched capacitor-based converters, and the next I'll be discussing on switched inductor-based converters. So all the purpose of all these converters are only to step up the voltage or step down the voltage to the required output voltages. And let me move on to the next one. It is transformers and coupled inductor based DC to DC converters. It is playing a vital role because nowadays the many researchers are working on this transformer and the coupled inductor based DC to DC converters, because when we go for high power application, so obviously we cannot go with switched capacitor and switched inductor. So the people will be focusing on transformer and coupled inductor based DC to DC converters. And the recent one we can call it's a Lua converters. It is like it is based on the multipliers, voltage lift and voltage multiplier techniques based converters. We called Lua converters, and the DC to DC multi-level or multiplier based converters. So then finally I'll be discussing on the future directions of DC to DC converters for vehicular applications. So after completing the session, so I'll be showing some the research work what I published on the DC to DC converters. So let me start the session. So as I told, the first session will be on the introduction part of the fuel cell vehicles. So as we know that the many researchers are claiming that the pure electric vehicles or hybrid electric vehicles are the very alternative solution for the internal combustion engine based vehicles due to the less utilization of fossil fuel. But I can say that the pure electric vehicles, a pure electric vehicle means it is based on the battery alone. So if it is a pure electric vehicle or the hybrid electric vehicles are using the batteries to drive the motor, right? So we have to charge the battery. So how to charge the battery? Obviously, we'll be using the commercially available supply. So those the supplies or those electricities or generator with the help of what your the coal maybe from thermostation or some other power station. So obviously I can say that the PEVs and HEVs are less eco-friendly when compared to the IC engine based vehicles. So in such cases I can say that the emission given by the pure electric vehicles and hybrid electric vehicles are much high compared to the internal combustion engine. So in that case, we can say that we have to look for some alternative solution. So the very efficient alternative solution is the fuel cell based power electric train vehicles. So here the fuel cell based vehicles are, it is gaining a lot of attention nowadays. So far, I cannot say that the fuel cell vehicles are dominating the pure electric vehicles and hybrid electric vehicles, but nowadays the people are more focuses on the fuel cell based vehicles. So I can say that the fuel cell vehicles and the hybrid electric technologies are gaining more attention in research, and they are going to play a vital role in the next decades, because now the lot of the automobile industries are started working on the fuel cell based vehicles. Even some the commercial vehicles are also available, so in the global market as well as in the Indian market also. So that's why the more research focuses on the fuel cell based vehicles. So the powertrain of whether it is a battery-based electric vehicle or hybrid electric vehicle or fuel cell vehicle, the powertrain will be giving a feasible solution to overcome the drawback of the IC engine-based powertrain. So I can say that the FCV, that is a fuel cell vehicles, is not only helps to maintain the healthy environment, but also reduces the services and the operating cost of the vehicles compared to IC engine vehicles. So as you know, maybe in nowadays, even the WhatsApp groups, some memes are coming like, suppose if all the vehicles are electric based vehicles, so the many people will be losing the opportunity. For example, I can say if it is IC engine based vehicles, we can say that the total number of parts is about more than 25,000 parts. But if the electric vehicle comes, so obviously I can say the major parts of the electric vehicles, it is only about 20 to 25 parts. So if that is the case, definitely so many people will be losing the opportunity. So I can say that the operating cost of the vehicle and the FCV also provides the healthy environment to the society, so that we can prefer the fuel cell based vehicles in future instead of going with the internal combustion engine based vehicles. So this FCV, why it is growing? So why that FCV is growing is it is because of the biggest advancement in the power electronics sector. So people are working. The so many researchers are thousands and thousands of researchers are working on the power electronics area, and daily, or we can say that per week, so many converters and inverters the researchers are proposing. So that due to that advancements, this FCV is growing like anything in nowadays. So the generation of electric power from the fuel cell is dependent on the type of fuel cells and the number of stacks and size of fuel cell. So as you know, the power generated by the fuel cell, it depends on the number of stacks. So how many stacks are there in the cell, and what is the size of the cell, and what is the capacity of the each cell, the power density of the each cell. So the generations depends upon all these factors, I can say. And the very big problem in the fuel cell is the working temperature. So that is a very critical parameter while selecting the fuel cell. I can say the critical working temperature and the type of electrolyte, which kind of electrolyte we are going to use it to make the fuel cell to work. So that is the very critical parameter. So that we have to check while selecting the fuel cell for your particular application. We have to check all these critical parameters. So now I'm coming to the classification of the fuel cell. So here, this classification is based on the usage, whether it is useful for the small electric vehicle or the large electric vehicle, and also the based on the power rating and the based on the temperature. This is the broad classification of the fuel cell. It is given here. So out of which, and here you can see the yellow shaded portion. So this yellow shaded portion, this is what useful for the small vehicles, or we can say that for small cars and small bikes, we can use the zinc air battery or regenerative fuel cell or direct methanol fuel cell. We can use it for small cars and bikes. Suppose if it is a passenger car, or if it is a passenger car, if it is a buses, or if it are trucks. So because now you see the people started using the fuel cell, the trucks also. So even the for buses also, if that is the case, we can prefer the reformed methanol fuel cell. And also this is the one of the very important member of the fuel cell, proton exchange membrane fuel cell, and alkaline fuel cell, and also phosphoric acid fuel cell. So these three are the playing a major role in the buses, trucks, and the big cars. So because you see the power density of these fuel cells are more, that you can refer here. You see, if it is a proton exchange membrane fuel cell, we can use it up to 1 watt to I can say it is 500 kilowatts. We can use a proton exchange member. And if it is the 1 kilowatt to 10 megawatt, we can use phosphoric acid cell. And also here you can see up to 200 kilowatts we can use the alkaline solar cell, so fuel cell we can use it. And so this is what so it's all these things are classified based on the power rating. So here you can observe the power rating. So as I told you already, here the one of the biggest member and one of the preferred member of the fuel cell is a proton exchange membrane fuel cell, because it can work up to 500 kilohertz kilowatts. And also you can see the temperature, it will work up to the temperature of 0 to 80 degrees Celsius. And also it can be work up to the versions of proton exchange membrane fuel cell also work up to the temperature of 300 degrees Celsius. And the power rating is good and the working temperature is good, so obviously we can prefer the proton exchange membrane fuel cell for the electric vehicle application. So I'm not saying that only that PEM based fuel cell is used. The researchers also using the alkaline fuel cell and also phosphoric acid fuel cell also for their vehicle applications. So apart from that, other fuel cells also there, but if we see the power rating is very less and also the working temperature is very less, we can say. And for the portable devices, we can use, I can say that some zinc air, or we can use solid acid fuel cell. All these things will be very useful for the miniaturized gadgets. We can use those kind of fuel cells. I can say the polymer exchange or membrane or proton exchange membrane fuel cell are the leading fuel cell technology, and it generates the electricity by utilizing the hydrogen directly from the fuel tank and oxygen from the air, and it emits only the water and heat as the byproduct. This is the very important thing. So this proton exchange membrane fuel cell will be utilizing hydrogen to generate the electricity, and also it takes the oxygen from the atmospheric air and it will be emitting only the water. So the excess part from this cell is only a water and the heat as a byproduct. So I can say that this fuel cell, that's why this is called the zero emission vehicle, due to the absence of tailpipe pollutant. And as I told you already, the PEMFC and alkaline fuel cell, zinc add battery, phosphoric acid fuel cell, and methanol fuel cell is suitable for vehicular applications. So all these things we can use it for vehicular application, but due to the high power density, the most of the researchers are focusing on PEMFC based vehicles. So that's because of the high power density. So not only the power density, it also you can check the temperature, the critical temperature, and the low corrosion and the regular storage and the robustness against shock and vibration. So because of all these advantages, the PMFC based fuel cells are preferred for the vehicular application. So initially when, because this fuel cell is not a new concept, I can say it is actually introduced in the year 1869 itself. And again, 1950, the improved version of fuel cell is introduced. And so far, I can say till the last 10 years, we'll be using it for the very slow speed vehicles such as submarine, forklift, and industrial handling vehicles. Only for those applications we have used fuel cells. But and nowadays, the people started using this fuel cell for the high-speed electric vehicles also, due to the advancement of powertrain of the fuel cell vehicles. So based on the structure of the powertrain, the fuel cell vehicles are classified into two different types. One, we can call it as a fuel cell electric vehicle, and the hybrid fuel cell electric vehicle. So these are the two different classification of the fuel cell electric vehicle. And the first one, you can say the fuel cell electric vehicle. So here you see you cannot see any kind of external storage devices. So here you can see this is what your fuel tank. So here it will be the hydrogen will be filled and the fuel reformer is there, and there will be a chemical reaction will be happening around here, and the fuel cell will be generating the electricity and it will be giving the DC power, and that will be given to the DC to DC converter. And again it has to be inverted, because mostly we'll be using permanent magnet synchronous motor to drive the vehicle, so we need AC supply. So obviously we need some inverters here. So this DC to DC converter will be supplying the regulated DC voltage to this converter, so that it will be inverting DC to AC and finally will be given to the motor. And also because you see the vehicles will be having some other loads also. because nowadays the most of the mechanical parts are converted as electromechanical, so obviously we need the electrical power supply to run those loads. Also we can say it is a medium and high voltage fuel cell support loads. So to supply those loads, obviously we need another DC to DC converter. So here you can see the another DC to DC converter, so it may be a unidirectional converter, and it will be supplying the enough power to the other loads apart from the motor loads, I can say. For example, if we have a AC is there, so definitely we have to drive AC, then we will be having the GPS system, will be having some charging system, and will be having some music players. So to supply all those loads, definitely we need a dedicated DC to DC converter. So my total focus is on this DC to DC converter. So here you can observe that there is no any external storage part. So that's why it is called fuel cell based. It is the standalone fuel cell based electric vehicles. And we have another classification also. So the next classification is a hybrid fuel cell electric vehicle. So here the why the hybrid name comes is that is because of this unit. Okay, this is the extra unit compared to this. So it is nothing but the battery and the ultra capacitors. So the battery maybe will be giving the enough battery, or the ultra capacitors will be giving the enough energy during the acceleration, the deacceleration of the machine, and also it is like a backup. It will be acting as a backup if the fuel cell cannot provide a supply to the motor drive system. So maybe the battery and the ultra capacitor will be giving the enough the energy or enough power to the motor drive to run the vehicle further. Okay, so not only that, we can say this battery system or the ultra capacitor system, it will be helping to increase the start of the vehicle, and also the overall performance of the vehicle will be improved if the battery system is provided. So the here the batteries and supercapacitor or ultra capacitors are adopted as an auxiliary energy source to support the fuel cell and to satisfy the power demand and supply requirement of the vehicle powertrain. So maybe during acceleration, the deacceleration, the machine may requires the additional power to drive the motor. So that time maybe the battery and the ultra capacitors will be playing a role, and it will be supplying the power along with the fuel cell system. And now I'll be moving on to this. So let me close. Yeah, so I can say the drawbacks and applications of the fuel cell vehicles and the transportation. So even though we have several advantages with the fuel cell based system, we'll be having so many problem, or we can say some drawbacks with the fuel cell technology. What are the drawbacks? So the very first drawback, or the challenge, I cannot say it is a drawback, it is a challenges. So the challenges are the poor hydrogen infrastructure. Like the electric vehicles, so we need to provide charging station. So similar way, we have to provide the hydrogen station. So here the infrastructure is very poor, the poor hydrogen infrastructure, and the complexity of the design, and the high manufacturing, the maintenance cost, because we need pure hydrogen to run a PMFC. So if that is the case, obviously the manufacturing and the maintenance cost is much more when we compare to the pure electric vehicles. So, and also the difficulties in matching with the performance of battery based electric vehicles. So these are all the challenges. So these challenges, so as a researcher, we can take any one of the challenge, we can work on that particular challenge, so that we'll do a lot of research on this fuel cell based vehicles. So coming to the application, as I told you, the application on the transportation system, the very first application is a passenger car. So for the passenger cars, as I told, the PMFC based fuel cell is mostly used. So as I told you already, in the global market, the companies such as the Toyota and Honda, even Hyundai also the leading industry in the development of fuel cell technology for the passenger cars. So here you can observe the passenger car system. So it is a very simple system, I could say a very simple passenger car. So here you can observe that the hydrogen tank is there and the fuel cell is there, and Here the byproduct is only the water will be come out of this, and also here will be having the power electronic system that will be given to the electric motor. This is very simple, the overview of or the block diagram of the fuel cell based the passenger car, you can say. And the very next one is the truck. So now, even now, the people using the fuel cell based truck. So here, this is one of the typical example or typical diagram of the fuel cell based truck. So here you can see the big truck is there, and here you can see the hydrogen tank, and behind this you can see the battery backup is there, and the electric powertrain. Here is the electric powertrain, and also the storage unit. Everything is the hydrogen storage unit. Everything is there here. So we can use it for truck. It is not only for the truck, marine applications and the aerospace applications. The aerospace applications, the people started using long days back itself. Okay, because you see, for the aerospace application, we need some kind of special requirement of the fuel cell, because the operating temperature, because of the different operating conditions, and also the low gravity. So based on that, we have to select the proper material for making the fuel cell. So it is not a new application, you can say. It is a very old application. The people started using in the year 1969. It's a 1969 itself, the people started using for aerospace application, but only for the few only for driving the fuel loads, and also the aircraft application. So these are the different applications of the fuel cell. Now, as I told you already, in the global market, we have the three companies. They are working on the fuel cell based passenger cars. The first one is a Honda Clarity, and the next one is a Hyundai Nexo, and the next one is a Toyota Mirai. So these three companies are working on the fuel cell based the electric cars. But all these three companies are using, as I told, the proton exchange member fuel cell based cars they are introducing. And if you see the power output of each car, so here you can observe that 103 kilowatts is a Honda Clarity, and the 95 kilowatts is maximum about 120 kilowatts. But in India, they launched a 100 kilowatts 100 kilowatts car here, and the Toyota Mirai, they introduced the engine with the 112 kilowatts. And there you can observe all the specification I have given. The very important thing what you have to note down here is, you see the electric motor, what type of motor they are using it for the fuel cell based electric vehicle. So almost all the three companies are using the same machine, the AC permanent magnet synchronous machine, only they're using it. And they are having the battery backup also. As I told, it's a hybrid based fuel cell vehicles. So we need the backup also, the auxiliary storage also required. So here the Honda and the Hyundai, they started using lithium ion, and the Toyota, they started using the sealed NIMH battery, they're using it. So, and also you see that you can observe the driving range of the each machine, or the each one. So the driving range is about, the Honda Clarity is about 590 kilometer, and also the Hyundai is about 610 kilometer, and also the Toyota, because the Toyota is the very first company they introduced fuel cell based electric vehicles. So but they got the driving range only about 500 kilometers. So in this I can say that the dominating one is a Hyundai Nexo Blue. So that is the dominating machine, dominating car. Even this Hyundai, they have introduced the car in India also. Actually they have they exhibited this Hyundai Nexo in the Auto Expo in the month of March 2020, and even the October 2020, they have done test drive with Hyundai Nexo. Maybe within 3 to 4 months it will be come to the commercial market in India. But these three varieties are available in abroad, so it is available. Even if we see the cost of all these cars, it varies from the $25,000 to $45,000. It will be varying, depends upon the version. And also even now the BMW is also working on the fuel cell based electric vehicle. If you see the BMW cost, the cost is about 85,000. It starts from $85,000. So they also started working on the fuel cell based electric vehicles, but these are the commercial vehicles which is available in the market. And here you can observe this is the first one, the Hyundai Nexo. This is the very first one. And so I just want to play a small video here. So here, actually this video is taken during that expo. So as I told, this vehicle is displayed in the expo, Indian Expo. And they have shown the internal structure of that Hyundai. Usually in the auto expo they will not show the internal structure of the vehicles, but in this particular expo they have shown the internal structure, how that the drivetrain system is there. So they have displayed that one. So for that purpose I just want to play this video. So just please observe this video so that you can come to know how what will be the different parts of the fuel cell electric vehicles.
Welcome to Power is मैं हूं आपका दोस्त.
But one problem is here, this is in Hindi, so please kindly bear with me. So because that review is given in Hindi only, so please kindly bear with me. So I hope the video is visible to you. You please watch it.
वीडियो काफी ज्यादा स्पेशल है. अगर आप एक हाइड्रोजन फ्यूल सेल इलेक्ट्रिक व्हीकल के बारे में जानना चाहते थे तो आपको इस वीडियो से काफी ज्यादा हेल्प मिलेगी. और आज मैं बात की है एक हाइड्रोजन व्हीकल नहीं है. पहले देखते हैं तो Hyundai की ऑलरेडी इन सेल कोना को जानते ही होंगे, जो कि अभी आप देख पा रहे हैं. इसकी जो प्राइस है लगभग 23 लाख रुपए एक शोरूम है. लेकिन आज वीडियो का मेन फोकस है हाइड्रोजन पावर्ड इलेक्ट्रिक व्हीकल्स, जो कि आप अभी देख रहे हैं. इंडिया में हाइड्रोजन के ऊपर बहुत सारे प्रोजेक्ट्स को ऑलरेडी रन किया जा रहा है. टोयोटा भी इस सेगमेंट में बहुत ज्यादा आगे है, जहां वो गोबर की चीजें मिलती है. हाइड्रोजन को मैं बताऊंगा एक फ्यूल सेल पावर्ड इलेक्ट्रिक व्हीकल यानी कि FCEV. पीछे आप देखेंगे इसमें सेटिन क्रोम फिनिश में आपको पूरा बम्पर दिया गया है, जिसमें आप इसके पार्किंग सेंसर्स को देख सकते हैं. ये व्हीकल ग्लोबली बहुत ज्यादा बढ़िया परफॉर्म कर रहा है. इसमें आपको बहुत सारे एडवांस फीचर्स भी मिलते हैं, चाहे बात करें इसके ऑटोनोमस ब्रेकिंग की, लेन असिस्ट, फ्लश डोर हैंडल्स के साथ आती है, जो कि आप अभी देख सकते हैं. और ये आप देख रहे हैं इसके पूरे कॉकपिट को, जिसमें आपको बहुत बढ़िया कंट्रोल, बहुत प्रीमियम टच मिलता है. और अगर मैं आपको इसकी सेकंड रो की सीट्स दिखाऊं तो ये है इसकी सेकंड रो की सीट्स. सनरूफ आपको इसमें मिलने वाली है. लेकिन इसका जो सबसे बढ़िया एक चीज है,
so this is the internal structure of the vehicle. So here you can observe the fuel tank. As I told, here you can observe the fuel tank will be there, and this is your power electronic system. So here they kept the bidirectional converter, and this is the fuel cell part. Maybe you can see in the
वो है इसकी
video.
ये है एक हाइड्रोजन फ्यूल सेल इलेक्ट्रिक व्हीकल, यानी कि ये व्हीकल हाइड्रोजन गैस से चल सकता है. ये देख.
So this is actually a fuel cell tank. Okay, so here the hydrogen will be filled up, and this is the filling part. So from here only they'll be filling the hydrogen gases, and here you can see the polytronic system, and this is your motor drive system. And here you can see the black color. So maybe I'll move on. So
सिलेंडर बहुत ज्यादा स्ट्रांगली बिल्ड है, अच्छी प्रोटेक्शन दी है इसके 100 किलोवाट के.
yeah, so here you can observe this is your fuel cell. Okay, this is your as I told, the proton exchange membrane fuel cell system is there, and here this is the pipe. Okay, through this pipe it will take the atmospheric air and it will take the oxygen, because you know this is a chemical reaction. We need a hydrogen and oxygen also, so it will take the oxygen from the atmospheric air. And also here you can see the compressor. It will compress the air, it will be given to the humidifier. Here it will be filtered, and the pure oxygen will be entered into the fuel cell system, and the hydrogen will be entering here. So a chemical reaction will happen, and also you can see the pipe which the water will be coming out of the system, right? So those pipes also you can observe. So that I'll show here.
फ्यूल सेल से अब फ्यूल सेल कैसे वर्क करता है, अगर आपने 9th या फिर 10th क्लास में केमिस्ट्री पढ़ी होगी तो आपको बहुत ज्यादा आसान होगा सब कुछ समझना. एनोड, कैथोड, इलेक्ट्रोड.
This is their overall power system, your polytronic system, the overall control system, you can say. So from here only all the controls are going. Okay, and maybe you can
लाइट, ये सब चीजें आप पहले से ही जानते होंगे, तो मैं आपको काफी इजीली एक ब्रीफ दे दूंगा कैसे पूरी चीज वर्क करती है. ये देखिए Hyundai का स्टॉल अपने सेगमेंट का एक बहुत अच्छा स्टॉल मुझे लगा, अगर जैसे मैं आपको फ्यूचर टेक्नोलॉजी बहुत आसानी से बता पा रहा हूँ. तो सबसे पहले सिंपली स्टार्ट करते हैं एक फ्यूल सेल वर्क कैसे करता है. उससे पहले आप जानते होंगे कि एक इलेक्ट्रोलिसिस प्रोसेस कैसे वर्क करती है. सबसे पहले मैं आपको ले चलता हूं कि ये व्हीकल की सबसे बड़ी एडवांटेज क्या है. जैसे कि हाइड्रोजन एक गैस है जो कि सबसे ज्यादा हल्की.
So one of the biggest drawback with the fuel cell based electric vehicle is the storage of the hydrogen. So as you know, the hydrogen is a flammable gas. So as everyone knows it. So for the fuel cell, what we have to do is we have to store the hydrogen with high pressure. So when we store the hydrogen with high pressure, so if any leakage, if any small leakage is there, so whether your system is so sophisticated and it's a very complicated structure, even if you made the very good system for storing the hydrogen, so that may be a small leakage will be there. So coming to the safety wise, this is I can say it is very less safe when compared to the battery based electric vehicles. But nowadays the people started working on how to store the hydrogen, because as you know, you can store the hydrogen either by gas or either by liquid hydrogen we can store. So the people are working on the liquid hydrogen storage also, but this is actually the gas storage, the gas based storage fuel tank. So this is made up of special material. So because as I told, with very high pressure the hydrogen is stored inside, so that is a very important thing. If it is not pressurized, then definitely there will be a lot of problems will be coming to the system. So that's why they have made with special material. Maybe you can observe now.
ये आपको इलेक्ट्रिसिटी प्रोड्यूस करती है। उससे भी पहले आते हैं कि इस व्हीकल को जो रिचार्जिंग टाइम होता है वो अंडर 5 मिनट्स होता है, यानी कि 5 मिनट के अंदर ये गाड़ी आपको लगभग 450 से लेकर 650 ले जाएगी आपकी हाइड्रोजन के। ये है इसका रेगुलेटर यूनिट, यानी कि यहाँ से जैसे आपके हाइड्रोजन जो मैक्सिमम प्रेशर जो टैंक के अंदर है, उसके बाद ये यूनिट आपकी प्रेशर जो कंट्रोल है उसको कंट्रोल करेगी, और कितना प्रेशर अंदर जाना चाहिए वो इसके सारा जो कुछ भी इसमें सिस्टम जो इसका कंट्रोलिंग यूनिट है वो सब कुछ कंट्रोल करेगा। और ये जो आप देख रहे हैं, ये देख रहे हैं आप इसका फ्यूल सेल स्टैक, यानी कि इसमें आपका कोई एक फ्यूल सेल नहीं लगा हुआ है। जैसे आपके घर में लेड एसिड बैटरीज होती है, इन्वर्टर में कार्स में होती है लेड एसिड बैटरी, उसमें मल्टीपल ऑफ सेल्स को सीरीज में कनेक्ट किया जाता है, यानी कि अगर एक सेल 2 वोल्ट बना रहा है तो 6 सेल्स को अगर सीरीज में लगाया जाए तो वो 12 वोल्ट आपको दे देता है आउटपुट पावर। उसी तरीके से इसमें भी मल्टीपल सेल्स को सीरीज पैरेलल ऐसे कनेक्ट किया जाता है और उनकी पावर को या तो ऐड कर लिया जाता है या तो इस पूरे सिस्टम की कैपेसिटी को बढ़ा दिया जाता है। तो सबसे पहले जानते हैं कि फ्यूल सेल वर्क कैसे करता है। फ्यूल सेल एक तरीके का अपनी परमिएबल मेम्ब्रेन्स होती है। अब ये मेम्ब्रेन क्या होती है? ये मेम्ब्रेन बनी होती है नोबल मेटल्स की, यानी कि गोल्ड, प्लैटिनियम और जो काफी ज्यादा एक्सपेंसिव मेटल्स होते हैं।
So this is the reason the fuel cell based electric vehicles are very high, because we need the membrane system is made up of the titanium. So the making cost of that membrane itself very high. So that's why the cost of the fuel cell based electric vehicle is too much high, because as I told you, it will start from the 25, even the Indian rupee can say 25 lakhs to even it go up to 60-65 lakhs also. So that's why the cost is because of the membrane, because we need a special material for that.
इसी कारण इस पूरे एक इलेक्ट्रिक व्हीकल की तुलना में एक हाइड्रोजन पावर्ड कार 2 गुना महंगी होती है। ये आप पहला पॉइंट पकड़ लीजिए। दूसरी चीज आप ये समझिए कि जो फ्यूल सेल है इसमें जो आपके मेम्ब्रेन्स लगी है, इसमें 2 साइड्स होती है, जो कि एक साइड एनोड को मान लिया जाता है और दूसरी चीज को आप कैथोड मान लीजिए। और ये फ्यूल सेल्स की जो मेम्ब्रेन्स है उनको सबमर्ज किया जाता है इलेक्ट्रोलाइट के अंदर। इलेक्ट्रोलाइट क्या होता है? एक आयंस को वो एक्सचेंज करने में बहुत ज्यादा इजी रहता है, वो कोई भी अल्कलाइन सॉल्यूशन। बाकी अगर आप एन गैस को एंटर करवाने के बाद आप यहाँ देखेंगे इसका जो इसका एयर फिल्टर है।
So this is what I told. So this is the pipe. So through this pipe it will take the air inlet and it will come to the compressor.
जितनी भी डस्ट और जितने पॉल्यूटेंट्स हवा में मौजूद है वो सब यहीं पर फिल्टर आउट हो जाते हैं, और जितनी भी फिल्टर्ड एयर है वो आपकी एंटर करती है इस एयर कंप्रेसर के अंदर। यहाँ पर आपका एक सेंट्रीफ्यूगल पंप लगा हुआ है। ये सेंट्रीफ्यूगल फैन आपकी एयर को कंप्रेस करेगा नियर अबाउट 1.5 बार, और उसके बाद यहाँ से ये एंटर करती है ह्यूमिडिफायर के अंदर। ये ह्यूमिडिफायर जो भी एक्सेस जो भी आपके सस्पेंडेड पार्टिकुलेट मैटर है उसको और ज्यादा रिमूव करके आपकी जो बिल्कुल फ्रेश एयर है जिसमें 21% के नियर अबाउट ऑक्सीजन है उसको एंटर करवाता है आपके फ्यूल सेल के इंडिविजुअल स्टैक्स के अंदर। और ये एंटर होती है कैथोजन गैस है, उसका ब्रेकडाउन हो जाता है H पॉजिटिव आयंस और सर्किट से स्टार्ट हो जाती है वो अनदर साइड आयंस के साथ। वो आपको देती है बाई प्रोडक्ट इस पूरी रिएक्शन का H2O, और जो इलेक्ट्रॉन आपके सर्किट में फ्लो हो चुका है वो आपको पावर देगा नियर अबाउट 100 kW, यानी कि 100 किलोवाट की पावर देगा। इसमें आपको एक बैटरी पैक भी मिलता है जो कि एज एन इमरजेंसी सिचुएशन, और जो भी चीजें आपको इसमें कूलिंग पंप, एयर कंप्रेसर, इन चीजों को चलाने में मदद करता है। फिर जो आपकी पावर जनरेट हो गई है 100 किलोवाट की, ये आपकी कंट्रोल की जाती है इसके सारे मॉड्यूल्स हैं जो कि इसकी आप हाई वोल्टेज असेंबली जितनी भी चीजें देख रहे हैं उनसे कंट्रोल हो गए, आपकी ट्रैक्शन मोटर को ये ड्राइव करते हैं और जिससे आपकी फ्रंट एक्सल को पावर जाती है। तो एक तरीके से ये था एक फ्यूल सेल व्हीकल का कि ये हाइड्रोजन गैस और ऑक्सीजन गैस को एक फ्यूल सेल में इंट्रोड्यूस किया जाता है। वहां पहले से ही आपकी मेम्ब्रेन होती है, इलेक्ट्रोलाइट होता है, और उसके बाद आपकी जब वो दोनों फ्यूल हाइड्रोजन गैस और ऑक्सीजन गैस इन द प्रेजेंस ऑफ कैटलिस्ट मिलती है, इलेक्ट्रोलाइट के थ्रू वो आयंस का एक्सचेंज होता है और आपके एनवायरनमेंट के लिए बिल्कुल भी हार्मफुल नहीं है, चले जाती है। आपने देखा होगा अपोलो मिशन के बारे में सुना होगा जो कि मून में गया हुआ था, वहां भी कुछ ऐसा ही।
Yeah, this is what your multi-directional, or I can say bi-directional DC to DC converter, which will be useful for driving the motor. Okay, so from here we'll go to the inverter unit, and there the inverter supply will be given to the motor, and it will drive the front axle.
एक तरीके से यूज किया गया था, लेकिन वहां ऑक्सीजन को लिक्विड ऑक्सीजन के फॉर्म में ले जाया गया था, लेकिन वो जिससे कि वो बिल्कुल प्योर फॉर्म में थी और जिसको एस्ट्रोनॉट ने ड्रिंकिंग पर्पस के लिए भी यूज करा था। तो ये कुछ था इस चीज को, यहाँ से इसका फिलिंग का आपको पूरा सिस्टम दिया जाता है, देख सकते हैं आप ये इसका, और इसको फिल करने में लगभग 4 से 5 मिनट लगते हैं। ये सारे टैंक्स को पैरेलली कनेक्ट किया गया है जिससे इसके प्रेशर को बिल्कुल इक्वल रखा जाए हर टैंक में। अगर आप टैंक के अंदर का कंस्ट्रक्शन भी देखते हैं तो ये देख सकते हैं बिल्कुल आपको
you see the pressure of the hydrogen is about 700 bar, so that's why I told, so high pressurized hydrogen is required.
मिलेंगे एल्यूमिनियम अलॉय, टाइटेनियम, बहुत सारे एक्सोटिक मटेरियल्स का इसमें कॉम्बिनेशन यूज किया जाता है, और इसका जो वर्किंग प्रेशर है वो है 700 बार्स का, यानी कि इस जिस एटमॉस्फेयर में अभी आप सांस ले रहे हैं उससे 700 गुना ज्यादा प्रेशर इन टैंक्स के अंदर रहता है। तो आप समझ सकते हैं कि कितनी छोटी जगह में कितनी ज्यादा गैस को ये लोग एक तरीके से कंप्रेस करते हैं। तो ये कुछ था एक पूरा इसका डिटेल, और भी जैसी डिटेल्स आएंगी मैं इसको आराम से और अच्छी वीडियो आपके लिए बनाने की कोशिश करूंगा। तब तक
So let me share my screen again. Yes, so I hope you understand how that fuel cell vehicles will be working. So obviously we need the power electronics. Without power electronics, it is not possible to run the system. So that much importance is there. So that's why I just want to give some overview on how that fuel cell based electric vehicles will be working. So this is, as I told, it's a Hyundai Nexo. And the very next one is a Honda Clarity, but this is not available in India. So only the very first the fuel cell car in India is only the Hyundai Nexo. Okay, so only this is available in the Indian market, but still it is not launched. Only they exhibited in the expo, and also they have done the test drive they have done in the month of October. Maybe soon they'll be releasing it in the market. Okay, so but this Honda Clarity, it is not released in India. Okay, but it is in abroad, it is available. And this is the very first car, I can say, the Toyota Mirai. So they are the very first fellows who worked on the fuel cell. So this is what the Toyota Mirai. So these 3 cars are available in the global market, I can say. So let me come to the bottlenecks of the fuel cell. The main bottleneck for widespread application of fuel cell is the high cost. Okay, so maybe you have observed in the video also. So to make that fuel cell, yes, we need membrane. So that membrane is made up of the high cost materials such as, you know, the platinum or the titanium. Mostly they'll be using a titanium. So the cost of making that membrane itself very high. So that the overall cost, not only that, you see the aluminum alloy or for to make the storage tank, we need aluminum alloy. So even that part also will take more cost. So because of that reason, the overall cost of the fuel cell vehicle will be much high when compared to the battery based electric vehicles. And the second problem with the fuel cell based electric vehicles is hydrogen storage. So now the people are working with gas storage, but maybe in future the people are working with liquid hydrogen also. Once compared to the gas storage, the liquid hydrogen is having less, I can say it's more safe than the gas. So that's why the people have started working on the liquid hydrogen storage also. And the infrastructure availability is another important prerequisite for, suppose if you are launching the fuel cell based electric vehicles in India, even we don't have any charging station for battery based electric vehicles. Only in the major cities we'll be having the charging station so that they can charge our battery based electric vehicles. But so far we don't have any infrastructure to have that hydrogen station. So that is the very prerequisite to introduce the fuel cell based vehicles in India. So this is, so the PEMFC is requires a high purity hydrogen which is not available conveniently elsewhere, but we can make the high purity hydrogen produced by hydrolysis, but it is a relatively very high cost when compared to other thing. So the investment cost per kilowatt for PEMFC is very high when compared to other fuel cell types, as we discussed earlier. So but the preferable one is PMFC, but it is very high when compared to other fuel cell type also. So one of the very big reason is, as I told, we need expensive materials such as platinum, okay, platinum or titanium or ruthenium. So all these materials, some expensive materials are required to make the storage tank and also to make the membrane. So in addition, the transport application portable items also requires a small system, and accordingly, the system needs to be miniaturized. So the later issue leads to high cost for tubes, compressor, control units, etc. So all these are the major bottlenecks of the fuel cell. So as a researcher, we can take any one of the problem and we can work on that problem so that we'll make good research on the fuel cell electric vehicles. So now coming to the next one, that currently we can say the battery based electric vehicles are ahead of the fuel cells. So even though we are talking about the more advantages of fuel cell electric vehicles, but still the battery based electric vehicles are dominating, because in the global market only the three companies are working on the fuel cell electric vehicles, that is the Toyota, Honda and the Honda. So it is expected that 2 million fuel cell based electric will be on the road by globally by 2030, because you know the Japan and South Korea, they are the leading researchers, okay, the leading manufacturers. They are working on the fuel cell. So maybe by 2030 we can expect the 2 millions of fuel cell based electric vehicles. And it is also believed that the phasing out of incentive schemes for the battery-based electric vehicles globally, which will, because from this year itself they started cutting off the incentive for buying the battery-based electric vehicles. So maybe in future they'll be giving the incentives for the fuel cell-based electric vehicles. If that comes, so definitely the fuel cell electric vehicles will pay more attention towards the researchers as well as the customers. So here you can observe this figure. So here you can observe the figure. So this figure is made up of, it is compared in terms of the truck usage. So suppose if you are going for the high distance, okay, if you are going for the large distance, definitely the fuel cell based electric vehicles are dominant than the battery based electric vehicles. But if it is a short distance, obviously the battery based electric vehicles will be the better advantage because of the cost. Okay, so for the small distance, I can say the cost of the BEV is very light, very less, so that we can say BEV is better for the small distance. But if we, for the small distance, the FC based electric vehicles are, you know, the very high cost, so that they cannot prefer for the smaller distance. If it is large distance, I can say it is more than 500 kilometers, obviously we can prefer the fuel cell based electric vehicles. So maybe in future the fuel cell based electric vehicles will be dominating the battery based electric vehicles. Now coming to the real taste of the power electronics. So what is the responsibility of the power electronics in this electric vehicle? So I can say that all the mechanical and the hydraulic loads are replaced by the electric loads. Okay, for example, now we people started using power steering system, power window system, power brake. Okay, for all the safety compartments, you know, for example, we have the airbag system. So for all those things, systems, we are not focusing on the mechanical loads or hydraulic loads. Now we are focusing on the electrical loads, right? So we need to power those things. So we need to give the sufficient power to drive all these loads. So for that, definitely we need a power electronics. So this is a very important point why we need power electronics for the electric vehicles. So therefore, the power electronics technology play a vital role in circulating the current power in a vehicle powertrain, and also to employ the advanced functionality and luxurious loads in vehicles. So the output voltage of the fuel cell is very low. So as it is very similar to your solar cell. So the output voltage of the fuel cell is very less. So if you want to increase the voltage level, what we have to do is we have to increase the number of stacks. Like number of cells we have to increase in the solar cell. Similarly, the number of stacks we have to increase in the fuel cell. So if you are increasing the number of stacks, obviously it is not the optimal solution to get the required voltage to satisfy the load demand. So what to do? Because the voltage is less, definitely I cannot increase the number of stacks because the system will be bulky. Obviously I can say the bulky system. So because we have to make the compact and comfort vehicle. So suppose if we give large space only for storing the fuel cell, then where we can sit, where we can drive. So in that point I can say that we cannot go for more number of stackings. We have to go with a less number of stackings, but I need a high voltage to drive my loads. Then what to do? So definitely what we have to do is we need a power electronics there. So the electric systems of the vehicle will becomes more complex and costly due to the electric loads. So in such cases, okay, in such cases, the power electronics plays a vital role and it is giving a reliable solution to implement all the application what I discussed earlier: air conditioning unit, the power steering unit, power windows, brakes, the safety requirements is nothing but your airbag system, your driver comforts. For all these things, the power will be delivered through the power electronic system. So apart from this, numerous high power electric actuation and dynamics are adopted to add an extra luxurious features to the vehicle. So these are all the responsibility I can say of the power electronics in the electric vehicle system. So now coming to the classification, this is what the very broad classification of the power electronic converter you can say. So obviously we need as you know, the power electronic converters are classified like DC to DC, DC to AC, AC to DC, and AC to AC. So now my focus is only on this DC to DC converter. So when we discuss the DC to DC converter, obviously based on the source, we can classify this DC to DC converter as a voltage source and the current source. But my ultimate aim is only on voltage source, so I'll not discuss about this current source. Now coming to the voltage source. Coming to the voltage source, yes, based on the operation, okay, based on the safety or based on the operation, we can classify the voltage source converter as the non-isolated and isolated converters, and each non-isolated and non-isolated converters are classified as unidirectional and bidirectional converters. Okay, as I told in the beginning of the session itself, I will not be discussing anything on the unidirectional or bidirectional converter. I'll be discussing only on the unidirectional converter. Okay, so when we come to the unidirectional converter, again there is a two different the outputs, like common grounded output and floating outputs. So because some application requires a common ground, that means the input ground and the load ground will be same. So some application requires the floating ground also. So for if you are taking the unidirectional converter, we can make the converter as a common grounded converter, or we can make it as a floating output converter. So that depends upon the user needs, we can make it. Okay, so now coming to this unidirectional power converter, again it is further classified into the single stage power converter, okay, and multiple stage or multi-stage power converters, and also DC to DC multi-phase power converters. Okay, so here my focus morely on the multi-stage power converters. So if you take a single stage power converter, it is nothing but your conventional converters. The conventional converters is nothing but buck converter, boost converter, and buck boost converters, right? So all these converters are not suitable to get the required high voltages, because if you want to get the required voltage, we have to adjust the duty cycle to nearby 1. If you are doing that, so what will happen? Definitely the reverse recovery issues of the diodes and the power switches will be more, so that it will lead to the less efficient system. So definitely we cannot use the conventional buck boost or buck boost converters for our application. So in order to rectify that problem, what we have done is we made some multi-stage power converters. In that multi-stage power converter also, we have the different classifications like the low voltage, medium voltage, and high voltage. So when we come to the low voltage power converters, low voltage multi-stage power converters, yes, we have a special converters called Chu converter, SEPI converter, and Zeta converter. Okay, so this is even we have Landsman converter also. Okay, here it was missed. So we have Landsman converters also there, but all these converters are made up of hybrid version of this buck boost and buck boost. Okay, so even though we made a special converters, so the problem with here this converter is, yes, we can get only the low output voltage. Okay, we cannot get the high step up voltage from these converters, because if you want to get the high voltage, again you have to adjust the duty cycle to maybe more than 90% of the duty cycle, again lead to some other problem. So only for the low voltage application, yes, you can go ahead with Chook converter, SEPIC and Zeta, because here the advantage of these converters when compared to this is, as you can say, that the output current is, yeah, so your input current is continuous. So because of that advantage, we are going with the Chook and SEPIC and Zeta converters. Yes, let me come to the next classification. Next is what we can say, it is a medium voltage converter. If it is a medium voltage, yes, we can focus on cascaded quadratic boost converter. So here the compared to cascaded boost converter, more focus nowadays is on the quadratic boost converter. Okay, so when we go with cascaded converter, as you know that we need multiple number of switches. So when the number of switches are more, obviously the gate drive system will be much complex. Obviously a lot of complexity will be involving to get the required voltage. So that's why they'll be moving to the quadratic boost converter, so that I'll be discussing later. Okay, so next I'll be coming to the very high step up voltage converter. Okay, it is based on the switched capacitor. So as I told, these are all your boosting techniques. Okay, these are all your boosting techniques, I can say. One is a switched capacitor, another one is a switched inductor, and next one is a transformer and coupled inductor based, and Lua converters, and also multi-level DC to DC converter and XY family. So this XY family, very recently, I can say in the 2020, the people started working on this XY converter based converters. Okay, so either the people will be going with capacitor, switch capacitor or switch inductor, or sometimes they'll be integrating the switched capacitor and switch inductor. They'll be calling it as a hybrid switched inductor and switch capacitor. So that's what here is mentioned, hybrid SI and SC. Okay, so based on the operation, yes, based on the output voltage levels, we can classify these converters. So now we'll be discussing one by one. So first, let me go with single stage and multi-stage converter. So this is what your single stage and multi-stage converters. So the very first figure, you can observe that non-isolated version and the isolated version. So here you see this is your input output. So both are non-isolated, both are connected here. Okay, but here you see the isolation. So there'll be isolation between the input and output. Okay, so it may be done through your isolation transformer, or I can say the high frequency transformer. They'll be isolating the input and output so that you can get the isolated outputs. Okay, so as I told, we'll be having the common ground and the floating ground, as I told, right? So here you can see the input and output will be having the common ground, but some application requires a floating output also. So here you can see that the ground is, this input ground is different, the output ground is different. So both will be different, so that we can call it as a floating output converter. So this is what single stage non-isolated converter, and this one we can call the single stage isolation converter. Okay, now coming to the multiple stages. The multiple stages means I'll be integrating, okay, I'll be integrating the boosting techniques what I discussed earlier. So I'll be integrating any one of the technique for my converter, so that I can call that converter as the multiple stage converters. Okay, so in multiple stage converter also, as I told, we'll be having the non-isolated and the isolator, and we'll be having a common ground and the floating ground. So it depends upon the user need. Okay, we can go with whether we need a common grounded multiple DC stage or a floating output multiple DC stage. Whatever is required, you can go ahead with that. So this is a very simple example for the common ground converter. So it is very simple. Boost converter, your buck converter and buck boost converter. Okay, so this is your simple boost converter. Okay, and here you can see this plus minus, this plus minus. So it means that the ground will be same. So you see the input and output, both the grounds will be same. Similarly for your buck converter, here you see this ground and this ground is same. But here the buck boost also, here you can observe this ground, that is input ground, and the output ground is same. So I can say these converters are, we can call it as a common grounded converters. Okay, now let me move on to the floating ground. So here you can observe that you see this ground. So this is the input ground, this is the output ground. So in the middle you can see the diode is there. It means that it means that your output is floating. Okay. So here your output is floating. So I can say that it is the floating output converter. So same boost converter, same buck converter and same buck boost converter. The only difference is the floating outputs. That's it. That is the only difference. So even you can also you can try all these kind of converters, how these converters working. And now let me come to the unidirectional multi-stage power converter. Okay, as I told, the non-isolated multi-stage converters are classified into low voltage step up. Okay, so low voltage step up and medium voltage step up and high voltage step up. Okay, so first let me move on to the low voltage step up converter. Okay, so here how that low voltage step up converters are made. As I told, the low voltage step up converters are nothing but your special converters called Chuk converter, SEPI converter, and Zeta converter. Okay, and also Landsman converter. So all these converters are low voltage step up multi-stage converters. How these converters are made? So as you know that these converters are made by hybridizing the conventional converters. Okay, so for example, see, suppose if you want to make a Chuk converter. Okay, suppose if you want to make a Chuk converter, what we have to do is, so here you can see this blue color line shows your output structure and this red color line shows your input structure. Okay, so this is C indicates your Chuk converter, Z indicates your Zeta converter, and S indicates your SEPI converter. Suppose if you want to make your Chuk converter, okay, suppose if you want to make your Chuk converter, what we have to do is your input structure is, your input front end structure is your boost converter, okay, and your output structure is your buck converter. Okay, so buck converter and boost converter. So the combination of buck and boost is nothing but your Chuk converter. Then next I will come to the Zeta. So the Zeta converter, here you can observe the input structure. The input structure is your buck boost converter and the output structure is your buck converter. So the combination of buck converter and buck boost converter is nothing but your Zeta converter. Okay, and if you come to the SEPI converter, the combination of, you see, the boost and buck boost. Okay, this is nothing but your SEPI converter. So here you can observe the figure. Okay, this is what your Chuk converter, and this is SEPIC converter, and this is your Zeta converter. So here you can observe that this is the simple structure of boost. Okay, and this is the structure of your buck. So we connected the buck and boost. So front end is boost and back end, that is the load end, is buck. So we made a Chuk converter here. Okay, and here when we come to the SEPI converter, so for SEPI converter, the front end structure is a boost. Okay, and the load end structure is the buck boost. Again we joined, we made SEPI converter and the Zeta converter. So when we make a Zeta converter, yes, as I told, here you can see Zeta converter, buck and buck boost is used. So the front end structure is a buck boost structure and the load end is the buck converter. So again the hybrid version of the buck boost and buck is nothing but your Zeta converter. So likewise we made the special converters, or we can say it is a low voltage step up converters. You see the voltage gain of all these converters are same. Okay, so all these three versions are act as a buck boost converters. Okay, all three versions are your buck boost converter. Okay, even the voltage gain is very similar to your conventional buck boost converter. Then what is the use of this? Yes, this kind of converters will be giving the continuous input current when compared to the conventional converters. That is the purpose the people are focusing on this kind of the hybrid versions. But the problem with this is, the voltage gain is very less. So similar to your conventional converter, the voltage gain is less. Yes, if you want to get more voltage gain, again, what we have to do is we have to go with high duty cycle. So when we go with the high duty cycle, yes, a lot of problems are there. So definitely we cannot use these converters for high voltage applications. So let me move on to the moderate or medium voltage converters. So here we have two different converters. One we called as a cascaded version. Okay, so here you can see the cascading. So this is converter 1, converter 2, converter n. So for example, one boost converter 1, boost converter 2, boost converter 3. So that I'll be cascading everything. Okay, then I'll be making the final output. So that, for example, you see, for this converter, the input is V in, output is V01. And for the second stage, the input is V01, output is V02. So likewise, your output voltage will be increased. But when you go with this kind of cascaded converters, yes, as I told you already, we have to use so many switches. Okay, for example, if you take one conventional boost converter, it is some 3 stages I'm using it. So obviously, for each stage we need one switch, one MOSFET switch or IGBT, whatever the switches you wanted. Okay, for each stage one switch is there. So if you want 3-stage output, yes, what we have to do is we have to use 3 MOSFET switches. So due to the increased number of switches, yes, the complexity will be keep on increasing. Yes, I accept that we'll be getting high voltage, but the problem is due to the large number of switches and due to the more number of inductors, because you see, for single boost converter we'll be using one inductor and one diode and one switch. Okay, if you use 3 stages, you have definitely number of inductors are more, number of diodes are more, number of capacitors are more. Definitely the system will be more robust. It will not be robust, I can say, it will not be reliable. Okay, so even though it gives high output voltage, but it is not preferable for the electric vehicle application. So in order to rectify that problem, the next version came that is called a quadratic boost converter. What is it, quadratic? Okay, here also you see the number of more stages will be there, but all the stages are controlled by only one switch. Okay, only one MOSFET switch will be there, but we'll be having n number of stages. That depends upon your output voltage range. Yes, you can increase the number of stages. Okay, but all the stages will be controlled only by the single switch. Here you can observe that it is only one switch is there, but we'll be having more number of stages. Okay, so the main, but what is the drawback of this? So because you see more number of stages are there, each stage will be delivering voltage, right? So the voltage across the switch, or we can say the voltage stress of this switch will be much high. Okay, maybe it will be equal to your output voltage. For example, if your output voltage is 400 volt, the voltage stress of that MOSFET switch will be 400 volts. So it means that we have to select high rating MOSFET switch. Okay, so if we want to select high rating MOSFET switch, again the problem is what is the cost of the system will be more. Okay, so this is why this is the major challenge in the quadratic boost converters. Okay, so let me move on to the high voltage devices or high voltage converters. So sorry, so high voltage converters, yes, as I told, it is having very high gain, a very high voltage gain. Okay, this is because of the hybrid version of the classical power converters with the different boosting techniques what I discussed earlier. The different boosting techniques, as I told, we have the switched capacitor technique or switched inductor technique or voltage lift, voltage multiplier, voltage doubler. Okay, we'll be having the coupled inductor and we'll be having a transformer. So with this different boosting techniques, I'll be integrating this boosting technique with my classical converters so that I can make new converters so that I can produce high voltage. Okay, this is what your high voltage converters. Okay, so what are the subclasses? As I told, these are the subclasses. Okay, so the switched capacitor based, switched inductor based. Okay, and also the hybrid combination of switched inductor and switched capacitor, and the transformer and coupled inductor based converters, and Lua converters, and multi-level converters. Okay, so first, let me move on to the switched capacitor based converters. Okay, so in this switched capacitor based converter, again it will be further classified into 3. One is with front end structure. Okay, the front end structure may be a buck converter or boost converter or buck boost converter. Okay, then there'll be the front end, they'll be having boost converter, and the load side end or between the front end and the load, they'll be connecting the switched capacitor so that they'll be making the multi-stage converters. Okay, this is one type, and the second type is without any front end structure. Okay, we don't have any front end structure. Okay, only with the help of switched capacitors we'll be making the converters. So that will be the second classification, and third classification is the switched capacitor will be there with the structure of the quadratic boost. Okay, as I told, the quadratic boost will be using only one switch, even though we will be having n number of stages, right? So that I'll be integrating with switch capacitor so that the multi-switched capacitor converter with quadratic boost front end structure will be proposed, and this is the future direction. Suppose if if any one of you is working on this converter, yes, you please focus on this, the multi-stage switch capacitor converter with quadratic boost front end structure, because you see the voltage is boosted with the help of switched capacitor, as well as a number of stages of quadratic boost, and also the voltage stress, because as I told already, the quadratic boost converter is having a problem of voltage stress, and that will be reduced when we have different combinations of the converter within the quadratic boost structure, so we can reduce the voltage stress. So this is the future direction of the power electronic converters. Please, if any one of you work on this particular topic, please focus on this particular title. So as I told, no, the switched capacitors. So these are all the different connections of switched capacitors. Okay, so when we talk about the switched capacitor, what will happen to switched capacitors? Okay, so in switched capacitor, what will happen? No, so we'll be having capacitors. We'll be having minimum of one capacitor. Okay, so not more than two capacitors. Okay, even only very few stages, I think only one of the researcher have proposed with three capacitors, but most of your switched capacitor cells are having two capacitors. Okay, so in this circuits, what will happen? No, all the capacitors will be charging parallelly and discharging series. Okay, this is the concept when we use the switched capacitor in your circuit. Okay, so whenever the capacitor is charging, that will happen through parallelly, and when it is discharging, it will happen series. Okay, so in this way, the voltage gain of the system or voltage gain of the converter will be increased. Okay, so what will be the overall gain of the system? So the overall gain or the voltage gain of the converter is depends upon how many capacitors you have used. Okay, how many capacitors you have used, and what is the arrangement? Okay, how you arrange the capacitor. Okay, as you have seen in the figure, we have given a lot of versions of the switch capacitor, so you have to select the particular version, which version will be suitable for your application. Okay, you select it and you just keep it, and whether you want to go with single stage SC or you want to go with two stage SC, so that you decide it, and you go just connect with your conventional converter so that you can make new converters. It is very simple. Okay, the proposing new converter is very simple. You take any one of this version, you take any one of your conventional converter, you just integrate it so that you can make one new converter. Okay, so don't be confused. Proposing new structure is very simple once you understand the working of all these structures. Okay, this is a switch capacitor based. Okay, this cells. Okay, this is a cell, and this will be connected with your conventional thing. Okay, how it is happening now, you can observe it. Okay, so in the switched capacitor base, we'll be having front end structure will be there. As I told, we'll be having with front end structure, without front end structure. So first I'll be moving on to with front end structure. So here you can observe the front end structure is the boost converter. You see, this is your boost converter. Okay, and this is your load. Okay, so between your boost converter and the load, I have connected one switch capacitor. Okay, so which type of capacitors I connected? You see, I have taken this circuit. Okay, I have taken this circuit, and it is connected with your conventional boost converter. You see, this is your conventional boost, and one stage switched capacitor is connected, and this is a load, so that we can make a new converter. Okay, in a similar way, and here also you can observe that one front end structure is there, one front end boost structure is there, and also this is two stages of switch capacitor. Not only a single stage, two stages are connected, so obviously the output voltage will be 2 times greater than your the first figure. Okay, so compared to this, it will be having more voltage gain because the stages are more, and also number of capacitors are more. Obviously, as I told, the voltage gain will be depends upon the number of capacitors and also the arrangement of the capacitor. So arrangement of capacitor depends upon number of stages. So here we used 2 stages so that the gain will be more when compared to this. Okay, and also here you can see the load structure. So 2 stages of SC network is there, and similarly here also you can see one input side filter is there, then output side capacitor is there. Okay, and in between, the load and the source, okay, we have connected another switch capacitor, so that you can observe this. You see, I have taken this. Okay, I have taken this, I just connected in between the input and output, so that I made one new converter. Okay, so likewise, you can itself propose your own converter. So these are all the different converters are proposed in various literature. Okay, so you can make use of this as a the base work, and you just try to propose a new converter so that you can also work. You can also propose a new converter for the fuel cell application, for fuel cell vehicle application. And so for what we discussed is, we have a front end structure. Okay, because in all the converters type, you see, mostly the front end structure will be boost converter. Okay, most of the converters, see, all the converters is having the front end structure as a boost converter. Okay, but the next one is without any front end structure, how the converters will be. So this is what the simple or some sample converters without front end structure. Okay, so here you can observe that the some number of switches when compared to this converter. So here you see most of the converters are having only one switch. Okay, most of the converters are having, I think almost all the converters are having only one switch. But when we come to this kind of converter classification, yes, with one switch it is not possible to get the required output voltage, so we need to use multiple number of switches. Okay, so as we discussed earlier, when we go with the multiple number of switches, okay, yes, the problem is what? The complexity. Okay, because each switch requires the isolated gate pulses. Okay, isolated gate pulses, you see, this is the pulses, it is, I can say, higher end pulse, but this one requires lower end pulse. Okay, so this requires lower end pulse, and this, so it means that different stages of pulses are required to turn on all the switches. So if you see the gate drive circuits, it is much complex when you design this kind of system. So yes, I can say that with the limited number of device counts, yes, we can make the converter with the high voltage. But the problem is, so many switches are there, the cost of the system, because 10 switches, obviously the gate drive system also complex, so the cost of the overall system will be it will be increasing too much when compared to the previous versions. Okay, and next I'll be moving on to the next structure. Yes, uh, this is the future. I told, no, it is a future version. So it is the integration of switched capacitor converter with the quadratic boost front end structure. So here you can see everywhere all the converters, most of the converters, the front end structure will be the boost converter, and I just connected some switched capacitor in between, but all the converters will be having only one switch, so that we can get more output voltage when compared to the previous structures. Okay, so these are some examples of the switched capacitor based converter with quadratic boost front end structure. Okay, quadratic boost means just one switch with multiple stages. So that is what the meaning of this. So if anyone want to work on this particular field, please focus on this quadratic boost front end structure. So next, similar to the multi-stage switched capacitor, we'll be having switched inductor-based converters also. So this is what the different switched inductor cells, and also the hybrid version of switched inductor and switched capacitor. Okay, so you can see all these first three. This first three is your switched inductor cells. Okay, you can see only two inductors, and minimum two diodes, or minimum two diodes are required. Okay, so so here also the charging and discharging will happen. Charging will happen parallelly, and discharging will happen series. Okay, so it's similar to your switch capacitor. Okay, so this is the pure switched inductor cell. Okay, and all other topologies are the combination of switched inductor and switched capacitor. Okay, as similar to your switched inductor capacitor, you take one conventional converter, you just integrate any one of your switched inductor cell, so that you can make one new version of the converter. Okay, so these are all the different combinations of switch inductor and hybrid switch inductor and switch capacitor cells. So you can make use of any kind of cell for your converter system. Okay, and these are all some examples of the switched inductor and switched inductor based converters. So the very first one is the conventional switch inductor. So here you can see I have taken one switch inductor. Okay, I have taken one switch inductor. Okay, and this is one switch. Actually, it just looks like what your conventional boost converter. You see, this is a conventional boost converter. Instead of one inductor, we just replaced with switch inductor. Okay, so we can make one multi-stage switch inductor based converter. Now what I'll be doing is, instead of this stage, okay, I'll be taking other circuit. Okay, I used this circuit. Now what I'll be doing is, I'll be replacing this with this. Okay, I can replace this. So if I replace this, you see here, I'll be getting the next stage. Okay, so it is, we call it as a hybrid version of switch inductor and switch capacitor. Okay, hybrid version of switch inductor and switch capacitor, and other stages are same. You see, other stages are same. So now, with the help of the switch inductor and switch capacitor, yes, I can increase the output voltage, because the charging and discharge will happen. Charging is happening parallelly and discharging is happening series. So series means, obviously, for example, here we have two inductors, so I can say my output voltage will be 3 times of my input voltage. I can say V in plus VL1 plus VL2, so that I'll be getting the maximum of 3 times of my input voltage. So likewise, it is based on the number of inductors and how the inductors are arranged within the converter. So based on that, the voltage gain of the system is decided. So next, I'll move on to yes, this is the another very important converter type. It is called a transformer and a coupled inductor based converters. Okay, so when we go with switch inductor and switch capacitor based converters, yes, the problem is we have to use more number of inductors or more number of capacitors and more number of diodes to get high voltage levels. Okay, but because when we use more number of inductors or more number of capacitors, yes, obviously the reliability issues will come. Okay, so now instead of going for switched capacitor and switch inductor, what we can do, yes, we can go ahead with a coupled inductor or transformer based. Okay, so we can reduce the total number of device as small as possible when we go with this coupled inductor based converters. So here the voltage gain of the system will be improved just by increasing the turns ratio of the coupled inductor. Okay, if I increase the coupled inductor turns ratio, yes, I'll be getting more output voltage. Okay, it's very simple. Okay, it is very efficient. Okay, we can get the required output voltage just by increasing the turns ratio. But the problem, what is the problem with this? Okay, that we'll be discussing here. Okay, so what are the problem with this? Yes, so before discussing the problem, I'll be telling you one more advantage of having the coupled inductor based. Okay, so because when we design inductor, yes, probably you'll be using more number of diodes. When we use more number of diodes, the problem with the diodes are reverse recovery issues, right? So all these reverse recovery issues problem will be rectified and will be removed totally by the leakage inductance of the coupled inductor. Okay, because when you design a coupled inductor, definitely you'll be having the leakage in the primary side as well as the secondary side. Okay, so that leakage inductance will be very obviously, the leakage inductance is having a problem. I'm not saying that the leakage inductance is having good advantage. Okay, the leakage inductance is having a problem. Yes, I accept it, but it is giving one advantage. What is that advantage? Is it will reduce the reverse recovery problem of the diodes. Okay, so this is a very big advantage of having the coupled inductor. But what is the problem with the leakage inductance? Yes, so because of the leakage inductance, the voltage stress, okay, voltage stress of the switch will be much high. Okay, voltage stress means the voltage across the MOSFET switch will be very high. Okay, you'll be getting a lot of spikes when the switch is operated. Okay, so yes, even though problem is there, yes, we can rectify it. Okay, how to rectify the problem? That's voltage spikes problem and all. Yes, this problem can be rectified with the help of your clamping circuits. Okay, when we have proper clamping circuits, yes, we can reduce that leakage inductance effect. So obviously, as I told, the leakage inductance is also helpful to minimize the reverse recovery issues. Now that leakage inductance problem is also minimized by introducing the clamp circuit, so that we'll be having a lot of advantage when we select the coupled inductor for your converter design and all. Okay, so these are all the different versions of your coupled inductor based or transformer based your converters. Okay, DC to DC converters. Okay, it's very simple. Okay, so here you can observe it is a simple flyback based converter. Okay, flyback converters, as you know. So it is a simple high frequency transformer. So here, one more very important observation is when we design a couple inductor or transformer based converter is that time you have to select a high frequency transformer, because as you know that when we go for the large power rating, we need bulky inductors or bulky couple inductor or bulky transformers are required. So because if you're operating the converter with less frequency, probably maybe 100 hertz or 500 hertz or 1 kilohertz, okay, in that particular frequency, if you are making big or if you are making high rated devices, high rated converter, yes, you need bulky transformer or bulky coupled inductor. Okay, so in order to reduce the size, what we have to do is we have to go with the high frequency transformers. Okay, high frequency transformers. So you know the high frequency transformers are made up of the ferrite cores, they'll be using it, powdered iron core, they'll be using it. So when we go with that kind of magnetic cores, yes, the problem is cost. Okay, the cost is the very big issue. Okay, because if, for example, I am designing one 100 watts converter. Okay, for example, I'm designing one kilowatt converter. Okay, for that, suppose if I'm operating that converter with 1 kilohertz frequency. Okay, if I'm operating the converter with 1 kilohertz frequency, yes, the problem is like we need a bulky size of inductor or transformer. But when we go with high frequency, only the small miniaturized transformers are required, so that we can reduce the overall size of the converter. So that is the biggest advantage when we go with high frequency transformer. So the organizer, if I have another 10 minutes, I will complete my session. You have another 10 minutes?
Sir, try to finish in 2 or 3 minutes, sir, because questionnaire will be there.
Yeah. Okay. So I'll just
right. 1 or 2 minutes, please. Thanks.
Yeah. So these are all the different varieties of couple inductor based converters, and this is also anyway when you go for couple inductor based, we have 2 winding couple inductor, 3 winding couple inductor. So all are these versions of the couple inductor based converters. So let me go to the lever converters. As I told, the lever converters means we'll be using lift technique. Okay, voltage lift technique, they'll be using it. They'll be going with the single stage lift, double stage lift, or triple stage, or 4 stage lift. So likewise, we'll be having the lift circuits are there, so they'll be integrating that lift circuit with the conventional converter, so that they'll be making lever converters. And the lever converters also will be having positive lever converters. Okay, it means the positive output voltage lever converters, and also you'll be having the negative voltage lever converters. So we'll be having different types of lever converters like this. Okay, and a multi-level or multi-stages converter. Okay, so the multi-level converters are having very big advantage, such as the less voltage stress. That is a very big advantage, with high conversion ratio, with less duty cycle. Okay, so that is a major advantage of having multi-level converters. If anyone want to work on this multi-level converters, you please focus on this area also. Okay, so usually how they'll make this multi-level converters, they'll be having the voltage multiplier circuit, such as Cockcroft-Walton voltage. This is one of the famous voltage multiplier circuit called Cockcroft-Walton circuit. Okay, what they'll do is they'll take the conventional converter, they'll take the voltage multiplier circuit, they will integrate it, they'll make the multi-level structure for your application. Okay, so these are all some examples of the multi-level converters. Okay, so you can see the level, so number of levels are increased. Okay, based on the load requirement, you can increase the number of levels. So that is the thing. And now let me come to the comparison. Okay, let me come to the comparison. So out of all these things, okay, so I can say the very efficient one, we can say one is a switched capacitor based and the multi-level converter based. These two are very advantage in terms of efficiency. In terms of cost, Yes, switch capacitor based is average, and in terms of reliability, yes, switch inductor is very high. Okay, but when we discuss about the high density or high power density, high power application, yes, we have to focus only on these three converters. When we focus on low power, yes, you can focus on these two. When you focus on high power, you please focus on the transformer, levo, and multi-level converters. Okay, depends upon the need. You can select what kind of configurations required for your application. And the future directions, okay, so the future direction, we have many kind. So my suggestion is you try to focus on multi-input and multi-output converters. Okay, multi-input converters or multi-output converters, and also try to use some special power electronic devices so that you can improve the power electronic converter efficiency. So these are all the future directions. And as I told, the quadratic boost converter, that is a very that is having best future. Okay, so you try to work on that quadratic boost and also multi-level converter, so that maybe the research purpose, that will be very useful. Okay, and these are all some of my recent work I published. This paper is we made some SEPI converter for solar photovoltaic system. This is actually published in IEEE Systems Journal. And this is another converter. Okay, it is another converter. So as I told, no, the couple inductor, this is what your couple inductor, this is how the couple inductor will be looks. And also this is the clamp circuit to reduce the voltage spikes in the system. Okay, and this is your converter. Okay, and this is actually proposed for some microgrid, DC microgrid application. Okay, and this is published in the MDPA Energies Journal. Okay, and this is one of the converter with multiplier cell, voltage multiplier cell, as I told, no, just we discussed now, with single stage voltage multiplier cell. Actually, this is a Cockcroft-Walton multiplier cell, so that I have integrated with conventional boost converter. And also here I have integrated the couple inductor. Also here you can observe the couple inductor also there, so that the output voltage, so here you see the input voltage is about 300, my output voltage is about 450. Okay, so that much high voltage application, high voltage you can get from this kind of voltage multiplier cell based converters. Okay, so these are some waveforms. And also, as I told you, the voltage spike, so here you can observe that voltage spike, very small voltage spike is there. So that is because I put one clamp circuit here. Okay, so even this converter will work without this clamp circuit also. If that is the case, the spike will be much more. Okay, maybe it will go up to this, so the voltage will be much more, so we need to select a high rating device. So that is a problem with the device which converter which uses the couple inductors. Okay, so actually this paper is published in Electrical Engineering Spring Journal, and these are all my recent publications with some good journals on different converters technique. Okay, so with this I would like to close my presentation. So I thank you all for giving this wonderful opportunity. So if you have any doubts, you please contact me, or if you want to work with me on different converter technologies, you please try to contact me, so that we can work broadly, we can work, and we can go for some joint research work also. Okay, so thank you.
Thank you, sir. Thank you very much.
Yeah.
Any questions, please, from the participant side? However, I will share sir's email ID. Sir, with your permission, I will share your email ID.
Yeah,
The
even I
participants?
displayed also, sir. If anyone wants,
Yes, sir, definitely.
if anyone wants, you please share with them.
Yeah, sir. Ramesh Solanki is going to ask one question.
Yeah,
Sir, please unmute yourself and ask the question.
Hello, sir.
yeah.
Sir, we are using so much component, and the voltage is increasing. But what about the current? Is there
Yeah.
any effect on the current?
Yes, so according to your ranges, okay, for according to your current range, you have to select the proper inductor. So suppose if you are using switched inductor based, you have to design the inductor that can withstand your required input current. Okay, for example, maybe the input current is about 10 ampere, means we have to design the inductor with minimum of 15 ampere, so that it can, even if any short circuit happen the converter side, it has to withstand, otherwise your windings will be burned and also short circuit will happen. So yes, that is possible if you select the proper device with the proper rating. So then obviously it is possible, you can do it.
Thank you, sir. Thank you.
Yeah.
Thank you, sir. Thank you for your wonderful session. And We are very, very much thankful to you for spending your valuable time with us.
Yes.
Thank you, sir. Now you can sign off.
Yeah. So thank you all. So thank you for giving this wonderful opportunity. So if you have any doubts, you please contact in my email ID. Thank you.
Thank you, sir. Thank you very much. Now I request all the participants. We have already shared the feedback link. Please submit it by evening 6 p.m. Okay, and tomorrow morning we will start the first session at 10 a.m. Fine. Thank you. Signing off. Thank you.